Alright, so this is the recording for some of the problems for the optics homework. I'm going to start out with the first two here that I only deal with conceptually, even though they do actually require a numeric answer. When you look at a mirror and you want to see your entire body from top of the hair to the bottom of the shoes, all you actually need is a mirror that is half as tall as you are. And it actually doesn't matter how far you are standing away from the mirror. And I think we can see that kind of in the drawing here. And what it is based on is the law of reflection, where the angle of reflection is the same as the angle of incidence. So we can see, for example, as the person here looks down toward the bottom of the mirror, and the mirror is just low enough so that he can see his feet, we can see that this part here is just half of his body from eyes down, and we can also see from his eyes up that is also just half to the hair up, and therefore the mirror here. And again, if you looked at the problem, you can do that with the numbers, but I just wanted to do that conceptually. The other one I want to do conceptually is the triple mirror retroreflector, and this would actually involve a proof of showing that the angle here under which it is reflected are such that the reflected ray, after it hits the second mirror, is going right back to where it came from. So if you only have one mirror, if you forget about this one here, then the incident ray would be simply refracted and it goes off. But now you put a second mirror there, and you can see by looking at the angles here, and this of course being a right angle, and noticing the relationships of the angles within a triangle, like this little triangle here, then right triangle in this case has to be, and then the reflected ray comes right back to where it was sent from. Well, why would that be? Actually, pretty important application. Usually these mirrors are produced in 3 dimensions, so you have a third mirror that is in 3 dimensions at a right angle to the other two here, and these are also called a triple mirror or a retroreflector. So let me pull it up. There we go. And that's what we see in reflectors that are mounted on cars and bicycles. And if we look at these hexagonal shapes here very closely, we can see that they are actually triple mirrors. And you see a bunch over here. Here's a diagram for 3 dimensions. And we can see them here over and over again. And yeah, that's what they're used for. There's also one on the moon that produces that is used as a retroreflector. In fact, there it is right there. All right, as I said, I just wanted to do the first two conceptually, and before I go on with the scuba diver, I'm just going to give myself a little break. All right, so this scuba diver who is in the water and sees the instructor standing on the side here, this would be the real scuba diver. This is the real person here, and he looks out and he notices the person over here, so this one is being refracted. When the refracted ray comes out of the optically thicker medium, it bends away from the optical axis being this one here. And the problem, it says that this one is 25 degrees. They didn't put that in. By the way, I don't know why they put in 2.0 meters twice. Actually has nothing to do with the problem. So anyway, this is 25 degrees. It bends away, so this angle here must be larger than 25 degrees. His optical illusion is such that as the instructor is actually standing over here and the light ray is bent, which he knows, but if he assumes that, hey, the person actually just follows the light ray, therefore the image kind of appears here, way up there. And for her, looking into the pool where the light ray is bending toward the optical axis, for her it seems like the diver is actually at a higher elevation. And again, I don't know why the depth and the distance are in here. Maybe there was supposed to be a follow-up problem for this one. Anyway, all it really is Snell's law. So here we have index of refraction times the sine of the angle equals index of refraction times the sine of the angle, one for air, the other one for water. So for one of the angles, which means you get the index of refraction over here, and you take the inverse sine, and then you plug in the numbers. So the 1.333 is for water, times the sine 25.0 degrees, because that's the angle underwater. If you look at what it says, you're training in a pool, what angle does the ray from the instructor's face make with the perpendicular water? The angle between the ray in the water and the perpendicular is 25 degrees Celsius. So it's this angle here. So that goes with the water. And then divide by the index of refraction of air, which is around at 1.000 for vacuum. It's exactly 1 for water. Top of my head, it's 1.00029, and that would be rounded, well, to what we have in front of us. And if we plug in these numbers, we ought to come up with the same result that they have here. So I'm going to take the, let's see, inverse sine of 1.333 times the sine of 25 degrees, or 25.0. Divide that by, okay, I actually don't have to divide by 1.00, close the parentheses, and I'm going to check if I am in degrees. I am, and I ought to come up with the same 34.3 degrees, and it looks like 3 significant figures. All right, going to give myself a break here. All right, I took a longer break, which was good because I was trying to understand this problem here, because this is about 3 pieces here: water, air, and polystyrene. And shouldn't I look at the boundary between water and polystyrene versus air? And then it finally occurred to me, as they were referring to 25.4, which is about the polystyrene, and where they do mention water to air, that the second part of the sentence right here is actually, should be in parentheses, that says at the end of example 25.4, which computes the critical angle for light traveling in a polystyrene pipe surrounded by air. So this is just the second part of the sentence here, really is only part of the example, not this particular problem at hand here. So my hose over here quite doesn't work, because if this was polystyrene itself, then it would have to be filled with water, which it's not. It's not about that, because then I still have to look at the boundary. Anyway, let me just do the problem. That's relatively simple. So again, Snell's law, and the critical angle here is that one of these two here, the N2 is 1.00, and then you have the sine of 90 degrees in there, because that's when the critical angle occurs. Sine of 90 is simply 1, so that one is gone from here for the critical angle. And then, yes, you plug in the other index of refraction for water in this case, so 1.33. So the way this one works, oh, look at that, I still have that from the other calculation. So I'm going to go here, there we go, and you know what, I'm just going to start over. Inverse sine of 1.00 divided by 1.333 parentheses, and I come up with the 48.6 degrees. I'm just going to look at this one here very quickly, the original problem, or the original example. Just a couple of things. One of them is this one apparently is a polystyrene cable here of some sort, fiberglass. And what threw me off at first is that the light ray should bounce from one edge to the other under the critical angle. But the way it comes in at the very edge, yes, then total internal reflection, and then again, and it just stays on one side because of the way they have the fiberglass bent here. And then over here, actually here, it goes from one edge to the other one. Again, simply because it's bent. That threw me off as well, actually. Okay, I'm going to go over to the book in just a moment. So let's see, where's the book? There we go. And here is the original problem, and then I'm going to go to example 25.4, click on that one. So this one is about the polystyrene, and yes, that's what they meant, this example about that pipe, that plastic pipe, and then they do mention the 48.6 degrees for water versus air, and then I do the problem. Anyway, I think I finally figured it out for myself. But one other little thing to point at is here they're saying that the polystyrene has a refractive index of 1.49. So I looked it up, And turns out, well, I guess depends on your source, right? So this one here is a certain kind of polystyrene that has been measured very accurately to 1.63 or 1.58 depending on the wavelength. And this dispersion within the index of refraction, we only mention that on the side. We just usually take an average value, but that's what you get when light is shining through some kind of glass or plastic, something transparent. The light actually splits up into its colors. So you get a rainbow out of that, a very narrow rainbow, which you usually don't like. So, I mean, it looks pretty once, but you want to use transparent materials and still get one light ray through it. And you have to get around that problem that actually the refractive index is dependent on the wavelength. The 405 that we can see, or actually 488, that's already almost the violet. The 405 is almost invisible to the human eye. The 633 is in the deep red. So these are the opposite parts. 514, 532, they're both in the green part. And yes, we can see slight differences in the refractive indices. Same thing for water. For water, it's even a little bit less. All right, took me 5 minutes for this particular problem because I had to mention quite a few things here. And we'll take a break again. All right, so I just put this one here that I figured out this problem. Did I not spell this right here? Really? Oh, yeah, there is a Y there. Okay, so here is actually the dispersion in the openstax textbook, and notice that, yeah, polystyrene is not the same as polystyrene, because they have quite different values from the research article I found there. I mean, there is a difference between 1.50 and 1.60 as the other one listed. Okay, now for this next problem, it uses actually from the same table the values for the crown glass here for a couple of these wavelengths. Let's see, it's the on this one here, the red and the violet. So it uses the 1.512 and the 1.530. Not that much in a crown glass, but crown glass, flint glass, these are typical glasses that are used in cameras, and they do have a certain dispersion value, and that's why you need a number of them, because you want to get rid of that rainbow distortion that you get there, which is called chromatic aberration, because otherwise your photos would look really strange. So anyway, that's why this one is important here. And yes, it does happen not just in the prism, but each piece of glass, any kind of lens, can be actually considered as a conglomerate of prisms. Light comes in, and then it goes out the other end at a different angle. So they have definitely this dispersion going on that you want to get rid of. Okay, so here it is. So how do they emerge? Notice that this one is a strange looking prism, I guess. It says 60 degrees here, so maybe if they do it equilateral, they're all 60 degrees. Anyway, the first relation here is just the way it emerges. Notice the way they drew the optical axis here, and we can see that the light ray is bent toward the optical axis, and then when it exits, it is bent away from the optical axis, just as it should be. It just looks a little bit strange the way they have it. So the first relationship right here, this is where they actually use the geometry for these kinds of triangles and figure out, okay, we have an inside angle of beta and inside angle of gamma, and how does it relate to the right angle that we have here for the optical axis, and then this corner angle here of 60 degrees. And they come up with this one here saying that once you have beta, all you need to do with it is subtract it from 60 degrees. This is what this algebra is about, and you figure out what that little angle gamma is. Okay, so now they're saying, okay, you got an incident ray here coming from air, which has in the refractive index of 1, coming in as at an incident angle of 45 degrees, and then you go through the motions, and you do that twice, once for the violet and once for the red. So let's see, this one here looks like it is for the red with the 1.512. So you come up with an angle beta, 27.8 degrees. You subtract that from the gamma, which is 32.1 degrees, and then you plug it in again as it exits over here, so the refractive one is 53.5 degrees. Again, if you follow Snell's law, you can easily do that. Here's the second one, so this one here would be for the violet one. So let's see, I wish that would be all on the same page. I don't know if I can do that. Oh, I know, because I added stuff up there. Okay, I was able to squeeze it onto just this page here. There we go. And so here's the violet one there. And again, it's the same thing. Figure out that angle beta in the diagram to 27.5. Subtract that from the 60, so you get 32.4. And then use Snell laws again as it exits, and you get 55.2 degrees. And I could show you that on the calculator, but we can also trust that the calculations are correct here. All right, so before I go on with this one here, I take another break. All right, changing gears. The next problem is about the thin lens equation, which itself, in order to figure out the focal length, is based on the lens maker equation, which includes the index of refraction, which includes Snell's law. So it all builds on the various aspects. Phenomena in optics. So here we have the thin lens equation, which relates the focal length, the image distance, and the object distance as reciprocals. That's just the way it is. Looks like adding resistors in parallel. The equation is really similar to that. In any case, as we have these three variables or parameters, if one of them changes, another one of the three has to change. So here we have given, respectively, if two are given, then we figure out the third one. So here it says you have a focal length, a fixed focal length of 50.0 millimeters in your camera lens. That's a typical lens to be used. And the image distance is actually relatively close to the film, which these days, obviously for the last 20 years already, is a charge-coupled device, so it's electronic. The object distance is usually relatively large compared to that, several meters rather than millimeters, of course. In any case, for a large object distance, I think you can see that if the object distance is relatively large, then this fraction here is relatively close to 0, which means di is almost the same as f. Yes, slight difference, 50 versus 51 millimeters, but that's what the focus is about. So yes, they are quite similar, yet they're relatively close. Okay, this one here, we're supposed to solve for the object distance, so dO over here. And I like to do it the way they're doing it right here. Subtract this one here, the 1 over image distance, you get this. And then invert this one here, hence you get it to the -1, that big parentheses. The reason why I like this one is because when I plug it into the calculator, I can do it all in one step. And if I need the equation again, well, I just have to hit second entry and get it back. Or if I make a mistake, then I just have to fix one thing. All right, so open the parentheses. 1 divided by the focal length was 50.0 millimeters. Subtract the 1 over the image distance, so 1 divided by 51 millimeters. Yeah, 51 millimeters, which is the image distance. And then again, because of the reciprocal, invert that one more time. Enter, and there we go. That's the 2,550 millimeters, which comes out to 2.55 meters. So the object is about 8 feet away. Then it wants to figure out what the height is. Well, the height on the film versus the actual object is a simple ratio between the height of the image and the height of the object versus the distance to the image and the distance to the object. And all these numbers are given here. So this is a 2.55 that we just computed. This one here then is the image distance. Hold on, I have to think about that. Oh, no, I'm sorry. This one is the image height. That's the 2.00 centimeters that they're saying here. That's what you get on the electronic part or the film, so 2.00 centimeters, which comes out to 2.00 times 10 to the -2 meters. And then this one here is given from earlier, the 51 millimeters, which is the image distance. And again, in meters here, 0.051. And then when you plug that in, you come up with 1.00 meters. That's how high the actual object is. So maybe you're taking a photo of a child that is about 8 feet away. The negatives that are in here, are that this negative here means that it turns it around. So it makes it upside down, and then they already put the negative in here for the image height so that we come up with a positive number for the object height, which does make sense, unless the kid is making a handstand. All right, again, a break before I go to the next problem. All right, and by the way, I wanted to point this one out here. So here's actually the camera. The focal length of the lens is fixed, and then this here would be the image distance from the lens to the film back here, or the electronics that you have there. And then you turn this part of the camera here in order to focus, and really what you're doing is actually you're either moving the lens away from the screen, from the film, or you're moving it closer depending on how far the object is, and that's how you get it into focus. They're comparing it here to the human eye. The human eye is doing it differently. It's not moving the lens away from the retina. That would be like you're squeezing your eyeball. I don't recommend that. Instead, the eye is it's a really interesting instrument. It has these little ciliary muscles right here and here that either squeeze the eye lens or stretch it, and therefore it actually changes the focal length of the eye lens, and that then puts an image into focus. And for some of us, it doesn't work as well. That's why we need eyeglasses or contact lenses. By the way, the eye lens is not the only part within the eye that focuses the image, or that refracts the light. It's the aqueous humor, it's the vitreous humor, it's the cornea. They all participate in that. But when we look at the simple optics that you find in a physics book, we pretty much just look at the eye lens versus the retina, and we go with that, which I believe is what the next problem is about. So here, what is the power of the eye when viewing a 50 centimeter object? So here it is. I just described this one here, and we have the two humors and the cornea and the lens, and then the retina in the back. So what is the power of the eye when viewing an object 50 centimeters away? So that's relatively close. You're kind of like reading a newspaper. And before I do the power, I actually simply say, hey, I'm actually going to do the thin lens equation, which is the power is 1 over f if it's in meters. By the way, down here I say that usually this is the way it's listed. Power is 100 centimeters divided by the focal length in centimeters. Okay, let's actually go from the top here the way I wrote this one here. So in blue, the openstax textbook reads, unless otherwise stated, the lens to retina distance is 2.00 centimeters. I found this one here in a different paper where it says actually this is 1.67 centimeters. Okay, let's assume it is the 2.00 centimeters in order to do this problem. So that's pretty much what this part here is about. Then, as I said, I'm using the thin lens equation. So 1 over f equals 1 over dO plus 1 over di. Then by the algebra, and I showed this earlier, you simply, in this case, as you're solving for f, just take the reciprocal, so the -1 shows up there, and then you put the image distance in there, 50 and 2.00, and then you should come up with the 1.92. So if I apply this one here, let's see, parentheses 1 over 50 centimeters plus 1 over 2.00 centimeters, that's the distance from the lens to the retina, and then take the inverse of that again to get the focal length. So in this case, 1.92 centimeters is the focal length of the eye lens, and if you focus at something else at a different distance, that would actually change the focal length of the eye lens, which again, that's the unique thing about the eye that we have, or that animals have, that we have these ciliary muscles that are able to stretch or squeeze the eye lens. 1.92 centimeters, and that I put into the diopter equation, so 100 divided by 1.92, I think you can believe that, divided by the answer here, is indeed the 52 diopters that you have. Wow, that is a large number. Oh yeah, it's about the eye. It's not about eyeglasses. Any case, notice actually that having done this up here would have been really straightforward, and it would have been the quickest, but I figure I might as well explain all the eye and the relationships there. Okay, again, take a break. So this is from chapter 26, problem 30, the microscope. So Namibia is this far away from an objective lens, in fact, just beyond the focal length. So the first lens actually projects a real image of that, and then we get an image that can be used as an object for the second lens, and that magnifies it even more. In order to actually calculate them, by the way, the answers are already in front of us. I figure I'm going to use an applet because a drawing is always advantageous. So I found this one here. Barb Newitt is a high school teacher in South Dakota, I think Sioux Falls. Anyway, she wrote many of these, and I really appreciate all the work that she and other people are putting into their GeoGebra applets. And so the way she set it up here is, she has the object on the left here, and she simply just used the arrow, and she put the bottom of the arrow over here on the optical axis, and then of course here's the arrowhead, so that we're going to get an image here, upside down of course, and, well, not of course, if it's inside the focal length, then the image actually will be right side up, as you see on the left hand side. And then final image here due to the second lens. So this can be used as a microscope, and I'm just going to show you a few things. You already saw that when I do something to the object, then all these principal rays and the images change the magnification as well as the principal rays. And notice she did use just 3 principal rays, and she color coded them. So these are not the colors of the light. She just color coded them so that you can see, hey, this is where this one ends up, and so on. The other variables that you put in here, you can change the focal length. And notice when you do that, short focal length, thick lens, long focal length, thin lens, same thing on the second lens here. And then yet another thing that you did is you can push that lens closer or further away from the first one. I think the first one here, she just wanted to have fixed at the 0 mark. So you can manipulate a lot of stuff here. And so I used that for the microscope, but here is the thing that happens. I think it's this one. Nope, it's not this one. It's this one. And my image, my object is way down here. There it is. And it just got out of hand when I tried that with this applet, among other things because magnification is so large. So I figured I'm going to do my own microscope thingy and make up my own problem, and that's this one here. So I'm going to go back, go one down. Here is the made-up microscope. Basically, it's the same thing. I just used numbers that I can actually use that applet for. So I made up these numbers here. So focal length 1 is 4 centimeters, focal length 2, 9 centimeters. The distance between the lenses is 30 centimeters, L for length, obviously. And then the object distance, 4.77 centimeters. So I just made up these numbers, and you can see that here. There's the 4.77. If you carefully look, there's 30. In fact, it says right there. Oh yeah, and then the applet actually says meters. I changed it all to centimeters. So whenever you see the word meters here, it's actually centimeters in my book. Then let's see, what was it again? Oh, focal length should be written down here somewhere. I saw it there. Oh, there it is. 4 centimeters right here. And the other one right there, 9 centimeters right there. Again, just imagine that it actually centimeters. Okay, let's do the calculations. And so I'm going to plug in numbers here. So this is for the lens on the left. I don't need that matrix thing from another class here. It was a tutoring session of another student. So here, thin lens equation, I have 1 over the focal length, so 1 over 4.00. and then I manipulate the thin lens equation, so I subtract 1 over the given object distance, so 1 divided by 4.77, and then of course that equals 1 over the image distance. So I invert that one more time and I come up with 24.78 centimeters, or 24.8, and we can see that here too. In her applet she has 24.7 centimeters. Could be a little bit rounding for her behind the scenes in her GeoGebra applet. That's why she's a tiny bit off there. Okay, so I'm going to go over here. I'm going to plug that in here. So 24, yeah, this is my made up one, so I'm going to call it 24.8 centimeters. And here I say, see the thin lens equation. I was too lazy to write that down again, so I'm going to go back to the previous problem, and obviously this is the equation that I just used. Okay. Objective magnification, by the way, that would be this equation right here, image distance divided by object distance. So the one I just calculated, 24.8 divided by 4.77. So 24.8 divided by 4.77. There we go. Or 7. Yeah, 4.77. There we go. Okay, 5.2. I think I did that one time in my head, so I change it, and the negative, of course, means that it's turned upside down. And yeah, I just used a magnification equation here. And actually, I think they made a slight mistake here. Both of these distances here are actually considered positive, so the negative actually appears in the magnification equation itself. It's negative. In fact, here, notice this one here? They put it right there. There it is. All right. So 5.2. Okay, eyepiece object distance. So next one, well, the image distance that I just had, subtract from L. So 24.8 subtracted from 30.0, which is 5.2 centimeters. By the way, the 5.2 here and the 5.2 here, that's just coincidence that these are the same numbers. Sorry about that. In case 5.2, and if we go back to the applet, then we can see that over here, again, she has a little bit different 5.29. So that's the new object distance for this other lens with the 9 centimeter focal length. So I'm going to use the thin lens equation again to get that image distance, this here being the new object distance, and I have to find my calculator. There it is. So I'm going to have 1 divided by 9.00, and looking at the sign conventions for object distances and focal lengths and so on, the thin lens equation didn't change at all, and what I mean is that the object distance is still a positive number, so when I subtract it, here of course I have it a minus. So I'm going to have 1 divided by 5.29 centimeters. There we go. Enter. And then again, invert, because it says 1 over image distance. I can already see that I'm subtracting a larger fraction, as I only divide here by 5, but the other one I divide by 9. So the second fraction is actually larger than the first, so which means I'm going to come up with a negative number here. So to negative 1 here, and there's my negative number, negative 12.83 centimeters. And when I go over here, we can see that's her answer in the applet, negative 12.81 centimeters. I just call it negative 12.8. And what it means is that this one now is indeed a virtual image, and that's because the former first image, which became the same second object, is within the focal length of that second lens. And so this one here is actually in a virtual image, but of course we can still view it, because over here we would have to imagine that our eyeball is actually here, and we're looking through it, and we're actually using our own convex eye lens to project that second image onto the retina as the third image, so to say. All right, so let's see, my answer was right there, negative 12.8 centimeters. Magnification, again, is the image distance divided by the, where is it, the object distance. Oh, there it is, yeah. So these two here, so 12.8 divided by 5.2. I think I will change this here very slightly. So 12.8 divided by 5.2, enter, so 2.5 this time around. Oh, I actually did write that, 2.5. And this one is a positive number, again, because the magnification equation actually does have a negative right there. And now I'm plugging in the numbers, but one of my numbers is actually a negative as it came out. Hence, the magnification in this case is actually a positive number, and all that means really from the drawing is that this image here is pointing in the same direction as the object from which it resulted. And then of course the very last thing is I multiply this magnification by that. So once again, negative 5.2 times 2.5. There we go. I think, oops, okay, shoot. What did I do? Negative 5.2, I forgot a times. There we go. Did I get it right? I think so. Negative 13. I did calculate that the other day, right? I think I guessed the other day when I did that. All right, so that's actually my made-up microscope. Now let's go to the microscope that came from the openstax textbook, and again the answers are already in front of us, and here is where the applet just isn't able to keep up with it because the numbers that result are just outrageous. One of the numbers that result, you can see that right here at the end, the magnification is minus 400. Again, the minus just turns around, which doesn't matter if you look at an amoeba upside down, but the 400 that's important, and that's of course what you use a microscope for. You know, mine only was a shift microscope. 13, that's not much. In a microscope you really want to have the 400, but that of course means that for the applet it just gets out of hand. So I tried to make the applet as close I can, and this was quite a thing to try as I get a focal length of 3 centimeters here to try to get an image distance of 3.05. Oh, I remember I just used the mouse and I almost cramped up my hand and so on. Apparently when we do that we get an image distance. Notice how much I have to zoom out. Apparently we get an image distance of, I want to say, is that 203 centimeters, I think. So that's kind of what we're going to get. Let's see. Yeah, actually it's 18.3. Again, the applet is a little bit off as far as the calculation is concerned for this one. So here the numbers that are given in the problem are, I'm going to clear this one here, so parentheses 1 divided by the focal length, so 3.00 is given, or it's actually 0.3, 0.300. Then I subtract 1 over the object distance from that, so 1 divided by 0.305, parentheses, and then again to the negative 1, so I can get the image distance. And there's the 18.3 that you can see right there. And then the applet, it's actually the 203 here. And I think the reason why I did that is in the applet, I had to go to a factor 10 anyway, because it wouldn't allow me to get to 0.3 something, you know. So I think, except for magnifications, my numbers here are 10 times as much as what there are in the original problem. All right, so I just confirmed this one here, the 18.3, then 18.3 divided by, that's the image distance, divided by the object distance, and I think we can see that that is 60 times, even if I don't compute it in the calculator. And again, the negative right here that we see right here actually belongs to the magnification equation. So the negative should be right here to begin with. So negative 60 times, simply turn around, hence the negative there at the end. And then subtract that image distance from the distance between the two lenses, and that's what it says here, is placed 20 centimeters from the objective. That's where the eyepiece is going to be. So 20 minus 18.3 is 1.7, obviously. Again, I don't have to use a calculator. In the applet, let's see, we should be able to see that. It's this one right here where she got 16.95. And again, it's 10 times in this applet that I had to use. I had to multiply everything with 10. So this is the same 1.7. So that's the new object distance. And I take that new object distance then and plug it in here with the focal length of the eyepiece. So 1 over the focal length of the eyepiece, which is the 2.00, which is quite a bit larger focal length than the objective lens. I subtract this new image distance from it. So the new image distance, oh yeah, that was the 1.70, so 1 divided by 1.70. Again, notice I will actually come up with a negative number. Whoops, typo. There we go, caught the typo. And you will see I come up with a negative number, which means the eyepiece is working as a magnifying glass. And so here, that of course confirms the negative 11.3. And when I go over here, that negative 11.3 turns out to, wow, I really have to zoom out, I think. Oh, geez. There it is. Again, with the shift of 10 times, this one here is negative 11.2. Virtually the same number that I just came up. Last time to look at this one here, by the way, when you, oh boy. Oh, I shouldn't zoom out all the way, so I can't get back in here. So when we look at this tiny object here to begin with, there it is, it's the orange one here, and then we look at the first image that the objective lens produces, which is this one here. I think we can see that that is the magnification of 60 right there, you know. And then we take this one here and we get it to this, I don't know, maroon color or something, and it's another 7 times or so, or almost, which then gives us that total magnification of 400. And I didn't attempt to measure this. The grid here is just, it's just impossible to work with. So I just believe, yeah, it is 400 even in this applet. So I just calculated here the 11.3, negative 11.3, and then plug it into the magnification equation for the eyepiece, and we come up with that, what I rounded a moment ago to 6.67 it is. Again, the positive here simply means that that second image is in the same direction as the first image. And then multiply this magnification here with that magnification, and you come up with that negative 400. Again, turn around the amoeba, or we don't care if the amoeba is upside down. One thing, by the way, I do want to point out for any of these applets, I forgot to mention that later. So she's doing a really great job in the way she programmed it. But notice that just like textbook images, I mentioned this probably before in other recordings, that the refraction is right here, and the refraction is right here. But in textbook images, or in this particular applet, you see that for some unknown reason, there is refraction right there, and that of course is not true, but it is really hard to draw when you do it on the board, and in an applet it's really hard to program to have the refraction right here, and to have it very dynamic as well. So I totally give her that she didn't program that, and the same thing of course happens here. Okay, I think I'm finally done with these two problems. All right, this one is quite an involved problem. Our openstax textbook likes laser surgery quite well. So we're saying, okay, so you have laser surgery, person has laser surgery, and you evaporate part of the cornea, and here they're saying, hey, let's make it easy on ourselves. Let's just say that the corneal tissue has the same properties of water, so we use the specific heat for water, which is the 4186 that we can see here throughout. And because it's evaporate, we also need to look at the latent heat of evaporation, which you would find in the book as 2.2 million right here, joules per kilogram. Okay, we need these two equations here. This one here is for specific heat, mass times specific heat capacity times the increase in temperature. That's from the 34 to the 100 degrees Celsius, as they say in the problem. And then we have to add the amount of heat needed in order to evaporate it, which is the mass times the, again, latent heat of vaporization. Okay, so they are wanting to know a brief burst, and so on and so on. Calculate the depth of the layer ablated, assuming, and so on. And so in order to do that, first they're figuring out what is the mass of the cornea that is actually evaporated. They come up with a very small number. And again, I can show you this one here in just a moment. So here they did just a little bit of algebra, figuring out what the mass is, and then they're going to use the mass and the density in order to figure out what the layer is, how much, what thickness is actually burned away, so to say. So here, after doing the algebra, it's the heat that is given here, 0.5 millijoules, divided by specific heat, which is 4,186, times the temperature difference to get it from, this is kind of like skin temperature, cornea temperature in this case, 34, up to the 100 degrees where water actually would evaporate it, so times the 66 here. And then you add simply the latent heat of evaporation to that. And if you plug that in, sure, here it is, we can see that we actually do come up with, so let's see, 5.00 times 10 to the negative 4, there it is, divide by, better open a parentheses for the denominator, so 4,186 times the 66 increase temperature plus the latent heat of vaporization. Let's see, that's a 6, there we go, parentheses, and of course that's what they come up with, the 1.975, 10 to the negative 10 kilograms. So this is where we're looking at something like nanograms, I believe, like 19 nanograms maybe, or even less. I think it's even less than that. Kilograms, grams, milli, micro. No, it is a few nanograms. Now here it says, okay, we're going to go with the density, and it's kind of like a cylinder, so to say. So pi r squared is a circle times the thickness. So the cylinder is being evaporated away, and then doing the algebra on that one is going to be the mass that we just calculated divided by pi and divided by the radius squared, and that should be in the problem here, the radius. Oh yeah, here, 1.00 millimeter in diameter, which means that it's 0.5 millimeters, which means 5 times 10 to the negative 4 meters is the radius. And this one here is the density for water, which is usually listed as 1.00 grams per cubic centimeter, but we need to have in standard units, so it's the 1,000 kilograms per cubic meter. And then again, when we do this one here, divide by parentheses pi times, I'm going to put that one in parentheses here, the radius, so 5 10 to the negative 4. And that, close the parentheses, that needs to be squared, there it is, times the density, close the parentheses for the denominator, and this is the thickness, that's the 2.5 10 to the negative 7. Oops, here they made a mistake. This one actually should say meters right here. That's meters, and here it's correct, micrometers, so 0.25 micrometers. Let's see, what was the second question here? Does the answer imply that the shape of the cornea can be finely controlled? This thickness implies that the shape of the cornea can be very finely controlled, producing normal distant vision in more than 90% of the patients. All right. Again, a break for me. All right, so this is about the bird feather. Structures on a bird feather act like a reflection grating, having this many lines per centimeters. What is the angle? The first order maximum for 600 nanometers. I changed this word here. It actually says reflection. Reflection. Boy, There we go, I got it. That's actually what it originally said, and I was figuring, no, that should say diffraction grating. Well, no, actually, reflection grating is correct. When you go to the diffraction here, and you come across the diffraction grating, they're actually talking about that kind of reflection, that grating actually being used as a reflection, like in a CD, as they say here, or in structures like feathers, where it's actually being reflected to you, but it still is a diffraction grating to begin with. And they mention the word several times here, so I'm going to go with this reflection grating. I just learned something new. Okay, so here we go. This one here is the diffraction equation. Pretty much everything is given here. It says it's the first order magnitude maximum, so solving for the angle theta means take the inverse sine, and then here again the m equals 1. This one here is the wavelength. The 600 nanometers is this much in meters, and then this one here is the diffraction constant, where it says 8,000 lines per centimeter, so a centimeter is 0.01 divided by the 8,000 lines that are given here, so we come up with this number. And again, all I have to do is plug it into the calculator, and I ought to come up with the same result that they come up with. So the inverse sine 1 times, then this one here is the wavelength, 6 10 to the negative 7, so that is between red and orange, kind of orangey, oops, didn't mean to close the parentheses, divide by the 1.25 that they had calculated, 10 to the negative 6, which is the diffraction constant. And then enter, and there's the 28.7 degrees that they came up with. Right, take a short break here. All right, and this is the last problem that I want to do about the eyes acuity. Notice there are several parts to this one here. So it says the limit to the eyes acuity, which is how sharp you can actually look at something that the eye can still resolve, is actually related to diffraction by the pupil. What is the angle between two just resolvable points of light for a 3 millimeter diameter pupil, assuming an average wavelength of 550 nanometers, which is kind of like in the yellow-green part, so in the middle of the spectrum. In order to figure that out, this one here is the Rayleigh criterion. Without the sign, actually, the sign is actually part of it, but you can leave that out for very small angles, because the sine of the angle is the same as the angle as long as you're in radians. That's why they do the radians here. So here, this one is it. The angle, or the sine of the angle, is 1.22 times the excuse me, the wavelength divided by the diameter. This one here is the 550 nanometers that are given in the problem, and this one here is the 3 millimeter pupil. And then when I do this kind of problem here, let's see, 1.22. That comes from the Rayleigh criterion. It's part of the formula equation. So 5.55, that's the 550 nanometers. So 10 to the negative 7, divide by the 3.00, 10 to the negative 3. Hit enter, and there is the 2.237, 10 to the negative 4 radians that they come up with. By the way, if I do include the sign, then I would get this, close the parentheses at the end here, and at the beginning, let's see, insert inverse sine, there it is, but I have to change the mode to radians rather than degrees. There we go. And when I do that, hit enter, same number, right? That's why for very small angles, as long as we're in radians, we can leave out the sign and just use that one. All right, next thing here is take your result to be the practical limit of the eye. What is the greatest possible distance a car can be from you if you can resolve its two headlights, given they are 1.3 meters apart? It's about 4 feet between the two headlights. So here they are using this relationship, which relates the radius within a circle and the angle to the arc length, and that the arc length, that would be the distance between the headlights. So, which is why right here for the arc length they would put the 1.30 meters in there, and then the angle, we already figured that out. For the pupil, it is the diffraction limit, so the 2.237, 10 to the negative for radians, and when you divide these two numbers you come up with 5.8 10 to the third meters, so 5.81 kilometers, which is about, oh, is that 3.5 miles? Yeah, it's about 3.5 miles, and you can still resolve the two headlights. I don't know about me, my eyes are not that good. I bet that at 3.5 miles I cannot distinguish between the two headlights. I mean, they still blur together, and of course they radiate. It's not like a point source, but they radiate outward as well. So, okay, anyway, the next part, so this must be someone with really good acuity, not me. What is the distance between two just resolvable points held at an arm's length, 0.8 meters from your eye? So that's about 3 feet away. Uses the same equation, but this one here says, okay, now we know, now we have given actually the radius here of this part of the circle times the, again, the radiance, and that comes out to this number here, which is the 0.179 millimeters. And now in the last part, they say, hey, can we actually compare that? And yes, if you hold up a ruler, apparently at that distance, you can actually resolve details that are 1 millimeter apart. So you probably can resolve even just a fraction of that, the 0.2 millimeters at arm's length. All right, and that was the last problem I wanted to do for optics.